Welcome back to the deep dive. Today, we're tackling something that, until recently, felt like science fiction. Building a generalist AI agent. One that can operate in these huge, complex 3D open-world games with, human-like skill.
We're going to be breaking down the open recipe for an agent called Lumine. And the whole thing was primarily trained in the world of Genshin Impact.
Right. And our mission today is really to unpack how Lumen pulls this off. We're talking about hours-long missions in real time, and then this incredible jump to completely different games.
It's all about that human-like paradigm. It has to see the screen, reason about what to do next, and then actually perform the actions.
Yeah.
All of that is unified in a single vision language model.
A VLM. And the results are really why we're doing this deep dive. Let's just start with the headlines because they are pretty stunning.
The big one is completing the entire 5-hour main storyline of Mondstadt in Genshin Impact. And it did this about as efficiently as a human player.
Okay, impressive on its own, but that's not the main story here, is it?
Not at all. The real shocker is the generalization. It then completed the entire first chapter of Honkai, Star Rail, a totally different genre, and a 100-minute mission in Wuthering Waves, all with zero, and I mean zero, fine-tuning. It just saw the new game and started playing.
That's the core of it. How do you build something that can handle that scale and that kind of jump? I know the researchers laid out six really specific challenges they had to overcome.
They did, and it shows how systematic the approach was. First, there's just the scale of the environments themselves.
Yeah.
Then you've got multimodal perception, mixing the 3D world with the 2D user interface.
Like your health bar and the mini-map.
Exactly. Then there's high-level planning for those long quests and the very precise low-level control of the character. Add in memory and the biggest bottleneck of all, real-time inference.
That last one feels like the make or break issue. A huge model like that, a 7 billion parameter VLM, trying to make decisions every 200 milliseconds. I mean, how do they stop it from just thinking itself to a halt?
This is maybe the cleverest part of the whole design. They call it hybrid thinking. The agent doesn't sit there and reason through every single frame.
It doesn't have an inner monologue running constantly.
No, it adaptively decides when it needs to think. If it's just walking down a path or fighting a simple enemy, it skips the heavy language generation step and just outputs an action directly. It saves a massive amount of time.
So it only pauses for that deeper thought when it hits a new puzzle or, a critical choice in a quest.
Right. It's how we operate. You don't deliberate on every footstep, but you do stop and think when you reach a crossroads you don't recognize.
Let's talk about the actions themselves. To get that smooth 30 hertz control frequency, you need to translate keyboard and mouse commands into something a language model can speak.
Yeah, they designed this very concise little action microscript. It's a token that represents, first, the relative mouse movement, how far to move the camera up, down, left, right.
And then the key presses.
And then 6 consecutive action chunks. Each one is about 33 milliseconds long.
Why 6? What does that get you?
It's because the model sees the world at 5 hertz, or 1 frame every 200 milliseconds. But to act smoothly, it needs to operate at 30 hertz. So it breaks that 200 millisecond window into 6 smaller chunks.
So it can model things like holding down a button for a specific amount of time.
That's the key. For a charged attack, it's not just press button. It's hold E for chunk 1, chunk 2, chunk 3, then release. It gives it that physical, time-based precision that you need for complex combat.
Okay, so that's the architecture. Let's get into the engine room. The 3-stage training recipe, it starts with just a staggering amount of data.
Stage I, the pre-training, was all about building that basic visual motor skill. They started with 1,731 hours of human gameplay. But, and this is important, they filtered out 95% of it, all the idle time, the camera jitter. They wanted pure, focused gameplay.
And this is where we see that hierarchy of skills emerge, right? You can actually see what's easy for the AI to learn and what's hard.
It's fascinating. Simple interactions like opening a chest emerged in under 100 hours of data. But basic combat and using the UI, like opening a menu, that took closer to 1,000 hours.
And the really complex stuff.
The deep game mechanics like elemental reactions or efficient navigation across the entire world, that required the most data, over 1,800 hours. It really shows that competence is built on a mountain of imitation.
Then we move to stage 2, instruction following. This is about connecting language to the actions.
Right, this was the alignment phase. They took 200 hours of higher quality labeled data to teach the model, which they called Lumine Instruct, how to ground its actions in simple language commands.
And then the final stage, stage 3, is reasoning. And this is the part that seems a little counterintuitive. After all that data in stage 1, the reasoning data set is tiny. only 15 hours.
Just 15,000 reasoning traces. And what that shows you is that reasoning isn't a skill you learn from brute force data in the same way. It's a strategy you learn to apply on top of the competence you already have.
So they just focused on human players thinking out loud during the first act of the game.
That's all it was. It taught the final Lumen thinking model how and, more importantly, when to generate that inner monologue for those really complex long-term plans.
Which brings us back full circle to the speed problem. You have this massive trained model, but it still has to act in under 200 milliseconds. How did they pull that off, technically?
They managed a 25.3x latency reduction over the baseline, which is just huge. They used a combination of things. First, memory tricks like streaming LLM, so the model isn't reprocessing its entire history with every single frame.
So it's focusing only on what's new.
Right. Then they used tensor parallelism to split the workload across 4 GPUs. And finally, some smart decoding tricks, quantization to shrink the model, and speculative decoding to sort of guess the next action quickly.
And the bottom line, in terms of time.
When it's not doing that deep reasoning, it can generate the next action in about 110 milliseconds. Well, within that 200 millisecond budget. That's the difference between a smooth, human-like agent and a jerky bot.
But for missions that last hours, you need more than just fast reflexes. You need memory.
It's a two-part system. It has a short-term memory, which is a flighting window of the last 20 steps or so. But the long-term memory is really clever.
Go on.
When the agent decides it needs to reason, it generates that new inner monologue, its new plan. Once that's done, it flushes the old context window and that new reasoning text becomes its long-term memory. The plan is the memory.
Let's get to the results on its home turf then. Genshin Impact, Mondstadt Act 1. How did it stack up against a person?
It had a 93.4% success rate on the mission, and it finished it in 56 minutes. The average new human player takes about 78 minutes.
So it was actually faster.
Substantially faster than a novice. And having that history context was key. The models with memory perform much, much better on things like puzzles and collection quests.
But what about when it failed? I'm always interested in the types of mistakes an AI makes. What were its gaming blunders?
They fell into 3 main buckets. The first was perceptual misrepresentation. This is basically misreading the screen, thinking it has more health than it does, or not seeing an enemy that's right there.
Okay, a simple mistake. We've all done that.
The second was premature completion. This is where it thinks it's finished a quest step when it hasn't. Like it talks to a character but forgets to pick up the item they drop and it just wanders off.
A kind of goal hallucination.
And the third, which is the most interesting, is causal misjudgment. This is a strategy error. The agent thinks if I use this ability, it will solve the puzzle, but it fundamentally misunderstands the game's physics or rules.
All right, now for the main event, generalization. First up, new quests within Genshin Impact that it wasn't trained to reason on.
It cleared the next 2 acts of the storyline, another 4.7 hours of gameplay, without any major issues. For example, it ran into a moving platform puzzle it had never seen before in a dungeon, and it correctly reasoned that it had to wait for the platform to arrive. It transferred the skill.
Okay, now let's leave the comfort of its home game. Wuthering Waves. Similar genre, but a totally new world.
This was a huge success. It finished the intro mission in 107 minutes, where a human novice takes about 101. So near human efficiency. The only real quirk was what they called domain bias.
Meaning?
It would use words from Genshin. It would call the enemies hilichurls or refer to the player character as the traveler.
So it played the new game perfectly, but with a heavy accent.
That's the perfect way to put it. And then came the ultimate test. Honkai. Star Rail. This is a massive jump in genre. It's a turn-based strategy RPG.
Not an open-world action game at all.
And this is where you saw the seams. It did finish the first chapter, which took about 7 hours, but it struggled. It kept trying to do things from Genshin, like jumping across gaps, which you just can't do in Star Rail.
And I imagine the combat system completely threw it for a loop.
It did. The whole real-time action script it had learned was useless in a turn-based system. It fumbled the keybinds, tried to use abilities when it wasn't its turn. It basically brute-forced its way through combat rather than using any real strategy.
So, stepping back from all this, what's the big takeaway from the Lumine recipe?
I think it demonstrates that you can take a relatively small open-source VLM and, with the right combination of large-scale imitation and a smart, explicit reasoning mechanism, you can create a genuinely competent generalist agent. It's the hybrid thinking that really bridges the gap between planning and control.
And the researchers obviously see a path forward from here.
Oh, absolutely. They're talking about scaling the data way beyond just the first region of the game, building better long-term memory systems, and maybe even integrating online reinforcement learning so it can
Mhm.
improve as it plays.
It really feels like we're moving from a purely theoretical space into seeing these agents work in really complex practical settings. So, what's the final provocative thought here? What's the biggest non-gaming door this opens?
Well, the researchers themselves point directly to game development. If you have an agent that can autonomously play through your game for hours on end, identifying where the logic breaks or where quests are confusing, you essentially have an automated tool for debug detection and quality assurance on a massive scale. It could change how games are tested, finding flaws that might take thousands of human play hours to uncover.